Hi! Welcome to another episode of Out of the Blue. Today we're talking about something really cool and pretty fundamental in astronomy, and that is light and time, and how these things right here are actually little time machines. So if you're ready, let's learn. The first thing you need to know is that light travels super fast, but it doesn't travel at an infinite speed. So it's like if someone's walking towards you, they don't get to you as soon as they start walking. It takes a little bit of time for them to actually get to you, right? Well, light does the same thing. It just goes so fast that we don't really perceive that time difference. Now, it goes 300 million meters per second, which is a huge distance, and it's kind of too big for us humans to comprehend because we live on such a small scale. But on the scale of the universe, that's not that much. So even the sun is far enough away that it takes 8 minutes for its light to reach us. So if the sun exploded right now at this very moment, you wouldn't know until after you're done watching this video and are probably moving on to more important things in your life. That might be a little freaky, but it's kind of cool to know that whenever we're looking at something far away, we're seeing it as it was in the past. And that's how astronomers time travel. That's how we look at the younger universe, just by looking really far away, because that means we're looking at things really far into the past. A term you might have heard floating around is a light year. Now, a light year isn't actually a measure of time, even though it has year in the name. It's actually a measure of distance. It's how far light travels in 1 year. Now, knowing that it travels 300 million meters in 1 second, you can imagine a year is a really big distance. However, our universe has been around for 13.8 billion years, so light has had time to travel 13.8 billion light years. That's the reason for what we call the observable universe. So if you're on one side of the Earth and you looked way, way, way far that way, you could see 13.8 billion years into the past, which is huge. If you looked 13.8 billion light years that way, you'd see the universe 13.8 billion years in the past. Now, the universe might be actually bigger than this. I mean, we don't know how big the actual universe is. We don't know if we can consider it infinite or really what to do with the size of the universe. But we have this observable universe because we can't see farther than 13.8 billion light years in one direction, because the light from that far away hasn't had time to get to us yet. It's still walking its way towards us, and it just hasn't caught up to where we are. Scientists and astronomers as a whole are really interested in looking at the baby universe to see what happened at the very beginning of everything, really. So we're really interested in looking at 13.8 billion light years away because that's looking literally at the youngest universe possible. We're looking at the universe when it was first being born, and that's really cool. What we found with that is that when we look all the way that way, like I said before, we find the same exact temperature as when we look all the way that way. Now, remember what I said about light being the fastest thing in the universe? That means information can't travel faster than the speed of light. That means the information of that temperature way that way could not have traveled the 27.6 billion years to get that way, because that's just too much time. Light can't travel that fast, and information can't travel that fast. So what that means is at some point in our universe, when it was first being created, it was all at a single point, and it expanded outward at faster than the speed of light. That doesn't contradict what I said before about nothing moving faster than the speed of light, because nothing in our universe can travel faster than the speed of light. Our universe itself has no bounds, really. Our universe can travel at whatever speed it wants because it's not bound by the laws of our universe. It is our universe. It kind of makes its own laws. It just does whatever happens naturally. Now, that being said, that's called inflation, and it's the main component of the Big Bang Theory that makes it the most attractive theory as to what happened at the beginning of our universe. That's kind of why we think the Big Bang Theory is pretty right, because no other theory combines this inflation thing with a plausible explanation. There's no other way for the information way over there to be the same as the information way over there. It just takes too long for that to happen. And I personally think it's really cool that we can see 13.8 billion years into the past that way, and 13.8 billion years into the past that way. We're seeing opposite ends of the observable universe that have never, for what we know, seen each other. And we know they actually did see each other at one point, but all other explanations besides the Big Bang say they've never seen each other. Even the Big Bang says they haven't seen each other since the birth of our universe. And that's pretty crazy. We're seeing the birth of our universe happen in a sphere around us, and we're watching it. We're looking at galaxies when they were first being created, and we're looking just that far away. And I just think that's really cool, because we're really time traveling just by looking at certain parts of the sky. Now, I talked about dark energy last week, and I said we knew that things were moving pretty fast in our universe. How do we know that? It has to do with the finite speed of light. So we know the light coming towards us kind of moves like this, and we know that it'll get our point no matter how this over here is moving, it'll get this to this point at the same time. Well, if this over here is moving fast towards us, then the waves in between have to kind of get closer together to like make up for that speed difference, because it has to reach us at the same time. The speed of light is so precise, it never changes no matter what the frequency of light is. So when things are moving towards us, we see all of the light from it at a higher frequency. That's called redshifting. The same thing happens when it's moving away from us, but we see a lower frequency of light. That's called blue shifting. And that's exactly how we tell how fast things are moving in the universe. We just look at a spectrum of the light, we see if the frequency is shorter, and we see if the frequency is longer, and that's how we know whether it's coming towards us, going away from us, and exactly at what speed. It's basically the Doppler shift, but having to do with light, and it's really neat. And light has so much to do with everything we do in astronomy because we look at everything. That's the only way we know how to see things. We wouldn't be able to see things super far in the past in our universe without light, because light goes the fastest out of everything in our universe. We can listen to things that far away because that sound hasn't had time to reach us. And that's the basis for all astronomy. Because of that, dark matter is super hard to detect. Everything we do in astronomy is based on light, and dark matter doesn't interact with light, which makes it kind of a butt to deal with. But we need to figure out how to deal with. And again, I'm going to tell you this every week. This is how you come into play. You need to figure out how to find dark matter, how to figure out more about dark energy, and how to play with light to figure out everything in our universe. Because there's a lot to learn out there, and it's our responsibility to figure it out. Have a great rest of your week, and I will see you next time. And please love science until then.